At the core of all stars, there's a glowing nuclear furnace. We can be sure of this because we can measure how many neutrinos are streaming out of the sun with experiments like the Sudbury Neutrino Observatory. This property of neutrinos, that they can pass through the core of a star virtually unimpeded, is because neutrinos are weakly interacting particles, which is to say that they do not interact with electromagnetic forces. Light particles or photons do interact electromagnetically, and thus they have a very difficult time leaving the core of a star. Let's carve into our own sun and examine how the energy produced at the core is radiated away as the light that we see here on Earth. The innermost region of the sun, extending from the center to about 1/4 of the radius of the sun, is the region where nuclear fusion takes place. This is aptly named the thermonuclear energy core. In this innermost region, the temperature, pressure, and density are extremely high, suitable for elements to combine in the process of fusion. The temperature has been estimated to be 1.55 times 10 to the power of 7 Kelvin, roughly 15 million degrees. The density of the material is nearly 14 times the density of lead, and the pressure is almost 1 billion times the atmospheric pressure here on Earth. Needless to say, you wouldn't want to go there, but if you did find yourself there, you'd want to escape pretty fast. In order for energy to escape from this region, it needs to be carried away by one of 3 processes: conduction, convection, and radiation. Conduction, which is the propagation of heat through a solid, is inefficient in the sun because, well, the sun isn't a solid. In this centermost region, extending to about 3/4 of the diameter of the sun, energy is carried away by radiative processes, the motion of photons. Extending outward from the thermonuclear energy core, the radiative zone is a region of the sun where photons dominate the energy flow towards the surface of the sun. You'd think that light, traveling at just over 1 billion kilometers per hour, wouldn't take long to escape from the core of the sun. And indeed, if there was nothing impeding the progress of photons inside the sun, they would take about 2.3 seconds to cross the sun's nearly 700,000 kilometer radius. But photons are impeded by the materials of the sun. Instead of 2.3 seconds, photons take an average of 170,000 years to escape into space. That's right. The energy we observe in the form of sunlight has been working its way to the surface of the sun for hundreds of thousands of years. Within the first 3/4 of the diameter of the sun, photons bounce around on very short paths, randomly walking their way towards the surface. Each step taken by a photon amounts to about 1 centimeter, and the energy must be carried nearly 700,000 kilometers. Just like the balls in this toy version of a rain stick, photons jostle through the materials of the sun, colliding and careening their way to the surface. Not every step will be directed towards the surface of the sun, though, but photons will preferentially migrate towards the surface due to the temperature gradient. If you consider that this rain stick has a gravity gradient instead of a temperature one, it's not a bad analogy for the motion of photons within the sun. Have a look at the math. If you took a 1 centimeter step every second, it would take you over 2,000 years to walk 700,000 kilometers. But that's assuming that you would walk in a straight line. If you stumbled around randomly, say after getting off a dizzying roller coaster, it would take you quite a bit longer to get where you want to go. Eventually, the energy from the core of the sun stumbles its way to the surface. From the centermost thermonuclear energy core, encompassing the first 1/4 of the sun's radius, through the radiative zone from 1/4 to about 7/10 of the sun, photons encounter the convective zone, the outermost layer of the sun's surface. As you move outward, the average temperature of the sun drops, and at the boundary of the convective zone, it's cool enough for electrons and protons to join into hydrogen atoms, which happen to be very good at absorbing photons. Radiative energy transfer is no longer the dominant process, and convection takes over. Atoms heated at the bottom of the convective zone become buoyant, and the mass of the hot atoms and plasma rise to the surface like bubbles in a lava lamp. cooler gas at the surface of the sun sinks down to replace the hot gas that's rising, and the process repeats. Once the hot gas reaches the sun's surface, energy stored in the heat of the gas is emitted as blackbody photons, which can then travel across the vast distances of space, virtually unimpeded. Now that there are finally some photons escaping the sun, let's put on our safe, solar filtering glasses and have a look.